This is a core block diagram for the PIC micro 16F1619. We are on this figure 2-1 from the datasheet. The core block diagram was explained in a previous lesson, but now we have to focus this lesson in the program memory, the program memory read, the PMR, which is where all the configuration of ports and registers is done. So we have to see all the registers and all the pages and how it works. Okay. So the memory organization. These devices, the PIC 16, 15, or 19, they contain the following types of memory: program memory, configuration words. Okay, the program memory is where the user stores all its code, all the code that it'll use for a specific program. It has a device ID, user ID, so those are words dedicated to print, we can say, to print an ID in that memory, to store it there. That way, when you read it again, you know which model, which version you are reading. And it has a flash program memory. The data memory is made of core registers, special function registers, general purpose RAM, okay, the common RAM also. And this device contains the program memory size, or the program memory space is of 8,000, we can say 8K, or 8,192 words, because it is 14 bits wide. And this is the last memory address. And the high endurance flash memory that it has is located in those addresses. And notice that this range is given in hexadecimal code. Okay, so this is why you see the H letter right here, the lowercase h, means hexadecimal. The high endurance is a small memory. It has 128 bytes. So that's replacing the previous E2 PROM memories. So this area is especially well suited for non-volatile data storage that is expected to be updated frequently over the life of the end product. Okay, and it has a limited number of reading and writing cycles. Okay, so we have to see the program memory map and stack right here. Program memory map and stack. And I didn't say in my introduction, I am Professor Jimenez, and we are learning this topic today. So the program memory map and stack for the 1619, it's formed by the program counter. The program counter is made of bits 0 through 14. The stack level is 16 locations, or 16 levels from 0 through 15. That means you can call and return from programs, from methods or subroutines, up to a number of 16 if they are nested. Nested means that once you go into a method, right there you are calling another one, and then you keep calling more instructions or more methods. Then that's how the stack starts getting filled with the return addresses. There is a reset vector, so when you turn on the device, a reset occurs in hardware and it'll send you to location 0000 hexadecimal. In other micros, the reset vector goes to the last location. For example, in other micros, it goes to 7FFF hexadecimal. But in this one, it goes to location 0. So, and there is an interrupt vector, which is located on location number 4. So you enable the interrupt and proceed to interrupt the program at any time. The program counter, this one, will jump directly to location 4, and from there you will make a go-to emergency, go to solve this issue, but now you know the program counter will go to this location. It has a linear memory made of 4 pages, and in this memory you don't need to change from page 0 to page 1 and so on, because it is a linear memory. In previous micros, there were 2 bits called RP0 and RP1, which were required to change the page number. Okay, so and before we see instructions, I know we have to see them. I need to show you here that when you are using the red L address, these instructions are used to add an index, so you can branch W and you can jump to any one of these locations, and then you return and load data. So load the accumulator with this data. So this is a way to store vectors of data, but we will see that in other applications. Okay, let me reduce the size of this. Okay, now we will go to the file select register, but we first have to see the data memory organization. So the data memory is organized in 32 memory banks with 128 bytes in a bank. So your bank consists of 12 core registers, 20 special function or SFR registers, up to 80 bytes of general purpose RAM, GPR, and 16 bytes of common RAM. So, and the core registers are these. Okay, the most important one is the program counter, low byte. Okay, the status and the file select registers. Okay, the working register is the most important one. And PCL and PC latch. PCL is the lower part of the program counter and the lowest byte. This is a high byte, low byte and high byte for the program counter. Okay, so now we have to go to the status. The status register is the most common register used in this microcontroller, the 1619. And the status register is shown in this format. It works this way. Notice that it has 8 bits. This is bit 0 right here. This space is bit 0, and bit 7 is right there. When you see a dash line right there in gray color, in gray shade, that means it is unimplemented, as you can see. So there's nothing here, an unimplemented bit, or red as 0. And the most important bits are the carry, decimal carry is 0, okay, power down and timeout. And the carry, to see the description of each one of these bits, you have to scroll down. So, and of course you can see here on the bottom part, you can see the carry or borrow bit. So it is used for those instructions, add WF, LW, which we will see later in another lesson. If the bit is 1, that means a carry out from the most significant bit of the result occurred. Okay. Only if there is a carry, you will get that bit equal to 1. So this bit, this one. If there is 0, if it is 0, no carry out from the most significant bit of the result occurred. Now another thing, when you see here R right here, in every bit you will see those descriptions. And let me amplify this a little bit. Okay, you will see those descriptions. I can move the page over there. So no, I will go back to 50. Okay, the decimal, the letter R means that you can read the bit, and the description is here. So that bit is readable. If you see a W /W, that bit is also writable. So it's a writable bit. And -0 is the initial state. So the bit is cleared when you power up the micro. That's the initial state. And /U, that means with a lowercase u right here, that means bit is unchanged. So sometimes the X is unknown, but the U is unchanged. But anyway, when you turn it on and you expect a 0 here, you have for reliable, to get a reliable code, it's better that you make sure that this bit is 0. So you just have to clear this file, all this file with a single instruction called clear file, or CLRF. And so every time you see RW, this is readable, writable, the initial state, readable, writable. But right here you see the right there, the R. So that means it's readable only. You can't write to this bit. You can only read it. And -1, so it'll start. The bit is set. The bit is 1 when you start. And Q value depends on condition. Okay. But you can read it only, and of course that'll be the initial state when you turn on the micro, when you apply power. Okay, and same thing for time all. So these are, we can say, outputs that you can read to know the state. Okay, and for those bits that I was explaining, the decimal carry, we saw the carry. Now the decimal carry, this bit, is a digit carry or digit borrow bit used for those instructions. So it is 1. If it is 1, it means a carry out from the 4th low order bit of the result occurred. That means this is for BCD operations, binary code decimal operations. Okay. If you haven't seen the BCD code, you can ask me that in the lesson, and I will explain it to you. The Z bit this is the 0 bit. The result of an arithmetic or logic operation is 0. You see, arithmetic or logic. If the result is 0, you get a logic 1 right there. And it'll start with logic 0 when you turn on power. And after you made an operation, every time you make a addition or Boolean operation, you need to clear it to make sure that it'll start again at 0. The following bit, which is located in power down, PD, the power down bit, a 1 is after power up. So in other words, it is equal to 1 after power up or by the clear watchdog timer instruction, or it is 0 by execution of the sleep instruction. Okay, so you can read them. If you are working with those instructions, you are allowed to read these states. The T0, this one, timeout bit is equal to 1 after power up, okay, by the instruction clear watchdog timer, or by the sleep instruction, which powers down the micro to save energy. And it's equal to 0. If it is equal to 0, a watchdog timer timeout occurred. And the watchdog is a hardware block. It's a hardware block that allows you to monitor the micro. So if the micro gets cycled in a loop, in an endless loop, and it doesn't return, the watchdog timer will indicate that, and that way you can get out of that loop and continue with the code. So this is the status register, okay? And there are other special function registers, which I will separate in another video about in our next video about bank memory partitioning and the special function registers. Okay, this is all for this lesson. Thank you.